Okay, so this is the outline of chapter 24 about the electric potential. So first we will talk about the definition of the electric potential, and then we will also mention something called the equipotential surface and the E field. Okay, so this is something related to the E field line, okay, introduced in chapter 32. Okay, so they have some geometrical relationships. So in this chapter we will talk about that. And then we will talk about how to calculate the potential, electric potential due to a charged particle, an electric dipole, and a continuous distribution. Okay, something similar to what we done in chapter 22. But at that time we are trying to calculate the E field rather than the potential. And actually the potential is a scalar field, so it will be easier to compute. And even for the continuous distribution case, for the E field, if you need to compute the E field due to a charge, continuous charge distribution, then you need to calculate the dE, and then you try to decompose it into x, y, z component, and then try to do some cancellation, and then try to work on the integration. But here, potential is a scalar field, so after you compute the dV, and then you just need to add them together just by a simple integration. You don't need to do any vector decomposition, so it will be easy. And then we'll try to calculate the field from the potential. Okay, just as what I mentioned, chapter 22, chapter 23, and chapter 24, all about how to compute the E field. Okay, so in chapter 22, you need to do the integration to calculate the E field. But chapter 23, we make use of the Gauss law so that the computation will be easy. And here we try to calculate the potential, which will be easier because it is a scalar field, and then we take an operation to that potential, then we will get the E field. And next, we will talk about the electric potential energy of a system of charged particles. So, yeah, so it's also another definition, and then finally, a potential of a charged isolated conductor. Okay, so first we will introduce another new variable called the electric potential. So it's set the electric potential V at a point P in the electric field of a charged object is defined like this. Okay, so it's a definition. So V equals to this negative W infinity over Q0, or equal to the U over Q0. Okay, so for the Q0, you can simply imagine it is just a test charge, a positive test charge there. And then here, what is negative W infinity and what is U? Okay, so simply speaking, negative W infinity is actually U. Okay, you can simply see that by cancelling the Q0 there. Okay, so here it says the W infinity is the work that would be done by electric force on a positive test charge Q0. Okay, where it brought from an infinite distance to P. And U is the electric potential energy that would then be stored in the test charge object system. So I think most of you are civil engineering students. You are quite familiar with the mechanics. So one of it is work done, one of it is the potential energy. Okay, so you try to bring a charge from infinite far away, so it has zero potential. So you try to do some work, you have work done on it, bring it close to another test charge. So you need to do some work, and by doing this work, you store some potential energy in this system. So that is quite simple, I think, to you. Okay, so here if you just look at the leftmost and the rightmost part of this equation, you can simply move this Q0 to the left side. So you have U equals Q0V. So here it is just written as U equals QV. Okay, just ignore the 0 there. Okay, so here is just mentioned that the U equals QV. QV. You can also consider is a definition, okay, because this part is also a definition. Okay, so that these two equations are actually the same. Okay, so here are some simple equation here. So the first one, delta U equals Q times VF minus VI. Okay, so VI and VF are defined to be the initial potential, and then the final potential. Okay, for I and F, one is the initial, one is final. So which means you try to move a charge Q from one point. Okay, so at this point it has a VI potential, and then move to another point VF. Okay, so if you try to move this charge from VI to VF, or actually the point I to point F, okay, you need to change the electric potential. You need to change the potential. Actually, the potential is not generated by this Q, it's generated by something else. Okay, here is just mentioned that if there is a potential here, and then if you try to move the charge from one point to another point, and we also assume that if you move this point charge Q, it doesn't vary the potential a lot. Okay, and in that case, so in that case, you need to change the potential, or the work done will be the negative to the change of potential. Okay, so here the third part is called the conservation of energy, 能量守恒. And actually it says if a particle moves through a change delta V in electric potential without an applied force, so which means it is a closed system, it doesn't have any work done to it. So applying the conservation of mechanical energy, so it gives you delta K equals negative delta U equals negative delta U. Or it should means that delta U plus delta K equals 0. Okay, so a system, the starting potential plus the kinetic energy equals the final potential and the kinetic energy. Or in the other way, you can also write it something like UI plus KI equals UF plus KF. Okay, so this is the initial potential and the initial kinetic energy, and then the sum of it will be the total mechanical energy at the final stage, which is UF plus KF. Okay, so in that sense, on the left side, it is a total mechanical energy at point I, and then the total mechanical energy at point F. But if you try to move over the terms, so it can be like UF minus UI equals KF, let's just say negative KF plus KI. Okay, something like this. Okay, so this one will be delta U, and then this one will be negative delta K, which will be something like this. Okay, so and the fourth case is if we have done some work on the system. Okay, so here we have work by an applied force. So it says if some force in addition to the electric force act on the particle, we account for that work. We account for that work. So in such a way, the delta K will be negative delta U plus the additional work done on it. Okay, if you put more work on it, then the kinetic energy will become larger. So it's that simple. Okay, so here we have a quick sample problem. So it says electrons are continuously being knocked out of air molecule in the atmosphere by cosmic ray particle coming in from space. 就是太空里面的话，就是有很多这种宇宙射线，就是在 Chapter 21的时候有提过，那个Gamma ray 那种，或者是 X ray 那种，是高能的粒子，或者是高能的光子Cosmic ray 就是把那个大气里面的一些空气的那个电子把它撞出去，就是然后就有一个电离的状态，所以就有一些自由的电子在那个空间里面 ，OK。So once released, each electron experiences an electrostatic force due to the electric field that is produced in the atmosphere by charged particle already on Earth. 所以在那一层里面的话，因为有电荷嘛，所以它本身就会有那个电场。那这个电场就会对于这个自由电子去施力 ，OK。Okay, near the Earth's surface, the electric field has a magnitude E and is directed downward. Okay, so here we have a E field directed downward. What is the change delta U in the electric potential energy of a released electron when the electrostatic force causes it to move vertically upward through a distance D equals 520 meters. So through what potential change does the electron move? Okay, so it will be easy. So work done will be the force dotted with the displacement. Okay, so you should be familiar with it. And actually the force will be Q times E according to the definition in chapter 22. For the E field, okay, so QE will be the electrostatic force or the Coulomb force, and then times dotted with D. Dotted with D. Okay, so actually it tells you that the electron is moving vertically upward through a distance. Okay, so the distance is the displacement vector is pointing upward and the E field is pointing downward. Okay, so here we have a QED and then cosine of theta, and actually this theta equals 180 degrees. Okay, so in such a way, this cosine of theta is -1, so it is nothing but negative QED. Okay, so in here we can plug in all the numbers. So negative Q is an electron. So it is negative 1.6 times 10 to minus 19. Okay, negative is an electron, so it has a negative charge. And then times E is here times 150, and then times D is here 520 meter. Okay, so in such a way it is 1.2 times 10 to negative 14 joule. Okay, so this will be the work done. Okay, but actually it asks you the change delta U, So delta U will be delta U will be negative W, which will be negative 1.2 times 10 to negative 14 joule. Okay, so this one should be the answer. And finally, it also asks you what is the potential change and what is the potential change. So for the potential change, we have delta V equals delta U over Q. Okay, so it will be actually, so maybe let me try to. Okay, so it will be negative 1.2 times 10 to negative 14 over negative 1.6 times 10 to minus 19. Okay, so it will be 4.5 times 10 to the 4th power volt. Or you can also write it as a 45 kV. 那这个就是45000伏，45000伏，就是比皮卡丘会比它厉害一点。Okay, so so this is a very simple sample problem. Okay, so any question? Okay, let's move on. So here we try to introduce the equipotential surface. Equipotential surface， 就是叫做等电位面，中文叫做等电位面。Okay, equipotential surfaces and electric field. Okay, so here it says that adjacent point that have the same electric potential form an equipotential surface, which can be either an imaginary surface or real physical surface. Okay, 所以它就是把这个相邻等电位的所有点，把它连接起来，它就变成一个面，变成一个面。那这个面的话，也可以是虚拟的，就是不存在实体的，也可以是有实体的。它就相当于那种等高线，不过等高线的话，它就是高度，所以在二维的平面上，它把同一个高度的点把它连起来，你就看到一圈圈的，或者是那种天气图有那个气压等气压的那个线你可以把它连起来，那它就是告诉你说，就是那个，比如说等高线的话，就告诉你是你的那个地形的高低怎么变化。那这边的话也是类似的，就是等电位面的话，就是这个是比如说一个是 V1、V2、V3、V4，它就告诉你那个电位是如何的变化。And yeah, so actually there. Okay, so actually it is related to the E field line, and actually the E field line, the E field line is actually perpendicular or orthogonal to the equipotential surface. 就是那个电场 E field line 啊，就是那个电场线会跟这个等电位面正交啊，或者你简单想就是垂直，那就是 E field line 经过那一个面的话，它就是在这一点跟这个面就是这个垂直的方向。那你说它弯曲的怎么垂直？你就是先求它的切面，那 tangent plane 求出来，然后跟它垂直那根线就是垂直嘛，所以大概是那个意思，啊。那工图不好，没有学过工图，所以不知道怎么画。Okay, so here it says the family of equipotential surfaces associated with the electric field due to some distribution of charges. So the work done by E field on a charged particle as the particle moves from one end to the other of path 1 and 2 is 0. Okay, so what it means? What it means? So it means that if you have a charge starting from here, okay, so this point is on the V1 surface. This endpoint is also on the V1 surface. Okay, if this charge move from this point to this point, okay, so the potential change will be 0. The potential change will be 0. It only related to the point, okay, the potential at the starting point and the end point. It doesn't relate to the path. Similarly, for path 2, this point is on surface V3. This point is also on surface V3. This part is actually moving along the V1 surface. But however, this path is actually moving from V3 down to V4 and then going back to V3. Okay, but still the potential change here is still 0 because it doesn't relate to the path. It only related to the final point and the starting point for the potential. Okay, so for V1, V2, the work done or the potential change will be 0. But for path V3, okay, the starting point is at V1 and then the end point is at V2. Okay, so here the delta U will be Q times V2 minus V1. Okay, so this is the final, this is the initial. And similarly for the V4, okay, so delta U3 and the delta U4. For the delta U4, okay, so the starting point also on V1, final point also on V2, but it goes a bit off and then going back. But still, it only related to the starting point and the end point. So these two will be the same. The potential change or the work done will be the same. And actually, it is equal to the negative W3 equals to negative W4. Okay, so the work done for path 3 and path 4 is not 0, but path 3, path 4 connect the same pair of equipotential surface, so they are identical for the two paths. Okay, so here we come up with a mathematical definition for the equipotential difference. Okay, 就是那个电位差。So the electric potential difference between 2 points I and F is like this. Okay, VF minus VI, but mathematically it will be like this. Okay, negative integration of E dot ds. Okay, so this is not a surface integral. This is not dA, this is ds. S is the somehow like the length of a segment, the length or displacement or displacement 就是一个位移的向量。Okay, so actually this is called a line integral, a line integral. So different from a line integral 线积分。线积分线积分。前面高 slow 的那个是surface integral， 是一个面积分，这个是线积分啊。线积分的话，就是说我在一个向量场里面，在这里当然是一个电场，然后在一个电场里面，我这个积分怎么积呢？平常你学一个一维积分的话，它是类似是 integration of f(x) dx， 这个是一个不定积分。那如果是定积分的话，它就是有一个上下限，那这个是我永远都是沿着这个 x 轴去直线的去做积分。那这里线积分不同的意思是，我会在一个电场或者是一个向量场里面，我有两个点，我有一条路径那我沿着这条路径去做这个内积就是这个电场每一点在这个路径上面我就把它切很多份切到底。那每一份的话它就是一个 ds 的向量。那在每一点在这一点的话，那个电场可能就是会长这样的，这个电场在这一点。那这个跟这个 ds 去做内积，就会得到一个 scalar。那所有段的那个到 ds 都会变成一个存量，那这些存量加起来就是这个积分。那最后加一个符号，它就会变成这个 potential difference. Okay, so this is the definition for the line integral. We try to separate the path into many small segments, and then we try to do the E dot ds for each part, and then finally add them together. Because E dot ds will become a scalar, so we add all the scalars together to become this line integral, the value of this line integral, and then finally take the minus sign will be the electrical potential difference. Okay, so this is the original definition for the potential difference or electric potential difference. Okay, so similarly, we can just write it as simple V. We can just write it as simple V. Or you can just consider it as a delta V, or you can just consider Vi to be 0. So V, we just let V to be the potential difference. So here we write it as a V equals to negative integration of E dot ds from I to F. So this is also the definition for the electric potential or electric potential difference. Okay, so here we have a special case, which is if we have a uniform E field, so this is really important, really important. Okay, so the change in potential from a higher potential, equal potential surface to a lower one separated by distance delta x will be delta V minus E delta x. Okay, so this one should be covered by the high school physics. Yeah, we just consider E to be a constant, and then so it turns out to be E ds cosine of theta. Okay, so the theta will be the angle between E and ds, and then finally we consider this one to be the dx. So it turns out to be a negative integration of from I to F, E times dx, and in such a way E is a constant, so we put it out, so it turns out to be negative E integration of dx from I to F, and then this one will be the length of that path, the length of that path. So finally, it turns out to be a multiplication. Okay, so this is another case that we try to integrate a constant so that this integration is nothing but a multiplication. Okay, so one thing forgot to mention is that the SI unit for V, SI unit for V is actually V, okay? So volt, V-O-L-T, okay? So this is voltage, voltage. volt 是单位 ，volt 是这个我们中文叫做电压叫做电压 ，volt 是单位。很多 PhD 学生都不会分 volt 跟 voltage 的，所以就是 volt 是单位 ，voltage 是电压，这个 V 本身。Okay, so in this way, according to this equation, so we have another SI unit for E. We have another SI unit for E. Okay, so if you have already practiced chapter 22, chapter 23, you should remember that the SI unit for E will be N over C, N over C. Okay, because we have F equals QE. Okay. So this is Newton, this is Coulomb. Okay, so E will have a SI unit of Newton per Coulomb. Here, according to this one is V. Okay, this one is meter. So the SI unit for E can also be volt per meter. Okay, so both are correct. Both are correct. Volt per meter and N over C, both are correct for the SI unit of E field. Okay, so here we have another central problem. So to let you familiar with how to calculate the line integral. Okay, so here it says the 2 point I and F in a uniform electric field E. Okay, so this is the point I, this is the point F. Okay, the points lie on the same electric field line, not shown. And are separated by distance d. Okay, so distance d. Find the potential difference Vi minus Vf by moving a positive test charge Q0 from I to F along the path shown, which is parallel to the field direction. Okay, the field direction E is pointing downward. Okay, the path is also moving downward. Okay, so in such a way we have Vf minus Vi equals negative integration of E dot ds and then from I to F. Okay, so along this path ds will be okay, ds will be all the way pointing downward. Okay, which means that ds and E are pointing to the same direction. So it turns out to be integration of E times ds and then from I to F. And as long as E is a constant, so we can move it out. So it turns out to be minus E integration of ds from I to F. So which is nothing but the length of this path. Okay, so the length of this path is nothing but d. So the answer is minus ed. Minus ed. So this is easy. Okay, so the only thing you need to consider is what is ds, the direction. Okay, so of course it is moving from I to F, so the ds should be pointing downward. Okay, so and then we have part B. Okay, so it says now we have the potential difference. Find the potential difference Vi minus Vf by moving the positive test charge Q0 from I to F along the path ICF. Okay, originally it is moving like this. Here we try to move from I to C to F. According to what I mentioned, the potential change or the potential difference doesn't relate to the path. Okay, it doesn't. It only relate to the starting and end points. So we should have the same. We should have the same answer. Okay, so but let's try to verify that. So for the first one, we calculate VC minus VI, so equals negative integration of E dot ds from I to C. Okay, so this is try to let you familiar with the line integral. Okay, so for this one, ds is pointing to the right side, E is pointing to the pointing downward. Okay, so so in such a way, E dot ds here will be a 0 because E times ds times cosine of 90 degree. Cosine of 90 degree is 0. So this one will be clearly a 0. Okay, yeah, because E and ds are perpendicular to each other. Okay, so next we try to compute Vf minus Vc. Okay, starting from this point, moving to this point. Okay, so it will be negative integration of E dot ds and then from C to F. Okay, here ds is here. Okay, so they have a 45 degree. They have a 45 degree angle between the E and ds. So in such a way, we have a negative integration of E ds cosine of 40 degree. And then from C to F. And then E is actually a constant. Also, cosine 45 degree is also a constant. So negative E cosine of 45 degree and then integration of ds from C to F. So which means what is the length of this path CF? Okay, so here we have a right angle triangle. This one is D, this one is D, and then this is 45 degree, this is 90 degree, this is also 45 degree, so this is also D. Okay, by Pythagorean theorem, this one should be square root of 2 times D. Okay, square root of 2 times D. So it would be negative E cosine of 45. Cosine of 45 degree is actually 1 over square root of 2, and then times this one will be square root of 2 times D. Okay, so square root of 2 and square root of 2 cancel each other, so it turns out to be negative ED. Okay, so finally, Vf minus Vi should be this one added with this one. So Vc and negative Vc cancels, so which will be negative ED plus 0, which will be negative ED. Okay, so we get the same answer. Okay, so far any questions?